In this section, we're going to talk about the kinematics of simple harmonic motion. We're going to lead into talking about simple harmonic motion in a couple of different situations, and eventually we'll look at wave behavior. But let's start with what is simple harmonic motion. Simple harmonic motion is anything that, or any motion that involves something oscillating back and forth in a regular interval. Things like pendulums, swings, tuning forks. Oscillating charged particles emitting electromagnetic waves, all examples of oscillations. And when we're talking about simple harmonic motion, it's important to know a couple of terms, and these are going to come up over and over again. The first is cycle. And a cycle is one complete oscillation, one complete back and forth of a pendulum, one complete up and down of an oscillating spring. When we're talking about it in terms of radians, which we're going to be using a lot in this unit, it's going to be one full revolution, or 2 pi radians. As an object goes through its oscillations, goes through its cycle, it's going to pass through what we call an equilibrium position. And this is where the object would be if it's not disturbed. This would be kind of like the rest position. With a swing, it's the position where the swing is just hanging there before you actually get on and start pushing it. Then we have the amplitude, which we symbolize with an x with a subscript 0, or x sub 0. And this is the maximum displacement from the equilibrium position. So we're going to be talking about displacement of objects, which is how far they are from equilibrium, but also the amplitude, which is the maximum value of this displacement. The period is a capital T, and this is the time it takes to complete one cycle. And then the inverse of this is the frequency, the number of full cycles completed per second, and this is what we measure in hertz. Now, in this unit, you're going to get to use radians. I know you're all excited by that. You don't get to use it very much outside of math class. Here's your opportunity. With radians, we're going to be talking about angular frequency. And angular frequency is similar to regular frequency, and we get it by using the regular frequency. It's symbolized with this kind of curly Q W looking thing, which is actually a lowercase omega, and as long as it's kind of got a little curl and a little tail, something like that, you're going to be alright in terms of writing it out. It's a lowercase omega, it's angular frequency, and this tells us the number of cycles per second in radians. Okay? So make sure your calculator is in radians when working with simple harmonic motion problems. Now, the actual motion that we're talking about here occurs when some system is oscillating back and forth at a regular interval. When we mean a regular interval, we mean that it has a consistent or constant period. So the period of each successive cycle or oscillation is the same. And one thing we find with objects that are in simple harmonic motion is that the acceleration is always in the direction of the equilibrium position. Now you're saying, well, if the acceleration is in the direction of the equilibrium position, well, that means the net force must also be in that direction. Bingo. This is what we call the restoring force. The restoring force, again, this isn't a new force. It's kind of like centripetal force. It's not a new force. It's simply an application of all of the forces that we've already been talking about. When we're talking about a pendulum, the restoring force is gravity. When we're talking about oscillations of a spring, the restoring force can be gravity or the elastic force in the spring itself. When we're talking about charged particles, it's the electrostatic force. So, the other significant thing about this restoring force, and also then the acceleration, is that it's proportional to the displacement from the equilibrium position. And so what that means is that as we get further from equilibrium, the restoring force increases, and thus the acceleration. As we get closer to the equilibrium position, the restoring force gets smaller, and so does the acceleration, until at equilibrium, the restoring force and the acceleration are both 0. Now let's look at our pendulum first. So we got two forces acting on a pendulum. We have the force of gravity, which is always acting, and which we're going to be working with a lot here. And that force, as we know, acts straight down over here, and in fact straight down here. We then also have the force of tension in the string that's partially counteracting the gravitational force, acting at some angle. And the idea here is that at any point where the forces aren't balanced, there's a net force acting back towards the center, or back towards the equilibrium position, and that's our restoring force. So over here it's in this direction, here it's in this direction, and that changes as we move along this path. What you should see is that in the middle here, the string is straight up, and so it's going to be perfectly balancing out the force of gravity, and so the two forces counteract each other, and the net force is 0. So as our pendulum passes through the equilibrium position, the net force acting on it is in fact 0. That's actually also where it has its maximum velocity. Now in the case of a oscillating spring, we have gravity still. Gravity's always there acting down. But our other force, our complementary force, if you will, is the elastic force of the spring. As we pull the spring down, that displacement from equilibrium stretches the spring out, and by stretching the spring out, we're increasing the elastic restoring force. And so if we pull it below equilibrium, then what that means is that the elastic force acting up is greater than the force of gravity acting down, and so the object is going to get pulled back up. If we lift the object up here, then it's going to have little to no elastic force, but the force of gravity will be the same, and so you can see that there's a net force acting down, so the acceleration will be down. If you have something just hanging by a spring and it's not moving, it's hanging at the equilibrium position. That's the point where the elastic force from the spring and the force of gravity are perfectly balanced out. Now let's look at the actual math associated with our oscillating objects. So let's imagine that we have a mass on a spring, and we start at position A. And we lift it up, and we're going to start graphing. And we let it go, and it's going to fall. It's going to pass through the equilibrium position O. This is where everything's balanced. On our graph, that's going to be the x-axis. It passes through the x-axis, the equilibrium position, and it's going to fall until it gets to B. At point B, the positive restoring force, or the force acting up, has sufficiently slowed down the mass so that it has a velocity of 0, and then it begins to accelerate back up in the opposite direction. So you can see it oscillating back and forth. It's moving down, then it's moving back up, and then it's moving back down. And notice that the length of these oscillations, the time length, is equal. Now our equation here, for displacement, and just to make a slight distinction here between our variables, x is our displacement at some time. X sub 0 is our amplitude, which is the maximum displacement. That's this thing right here. That's this level here. And so at any given point, our displacement is the amplitude, x sub 0, times cosine of omega t. Now this cosine omega t is basically telling you where along this graph, where along this position graph you're looking. And so the cosine omega t moves you along the graph to show you what portion of that maximum amplitude you're at a given time. And here we have omega, which is our, remember that's our angular frequency, and you have your time. So the cosine of the angular frequency times the time times x sub 0. And notice also this is a displacement graph, and so we are going to have positives and negatives. Anything above the x-axis is a positive displacement. Anything below it is a negative. So a little bit more on this, and just kind of reiterate some of the things we talked about. The displacement is a function of time. And so we have x equals x sub 0 cosine omega t. And omega is the angular frequency. T is the moment in time that you're looking at. As we said, this function omega t puts us at the point along the curve. And as I mentioned before, make sure that we switch our calculator to radians when we're working with simple harmonic motion. And then when you go back to algebra or whatever class, don't forget to switch it back. Then we have our velocity graph. And the velocity graph is related to the position graph. And we're going to talk about that in a few minutes. But if we look at our velocity graph and we kind of remember back in our heads what was going on in the previous graph, in the displacement graph, our displacement graph started, remember, up here and traveled down and went to here and then up and here, down. Okay? And so what you should notice is that when the object is at its maximum displacement, so at t equals 0, for instance, it's at its maximum displacement, it's at its minimum velocity, so velocity is equal to 0. When it's passing through the origin, the displacement is 0, but the velocity is at its maximum. And then it travels back here, it gets to the other side, and again, the velocity is at 0. So at the maximum displacement positions, the velocity is 0. As it passes through the origin, the velocity is at its maximum. And again, you can relate these to the gradients, just like when we were talking about translational motion. The velocity of the motion, or the velocity of the motion of the object, is the slope of the displacement time graph. Same thing here, when we're talking about displacement and velocity, those rules don't change just because we're talking about a different type of motion. The slope of the displacement time graph still gives us the velocity. And thinking about that, here's the slope at our maximum displacement is 0, and our velocity is 0. Let's pretend that's a straight line down. Now, we're not going to use this graph because it's not a great picture of it, but you should notice, here we go, this is a better graph. If we look at our acceleration, or excuse me, our displacement here at the top graph, and our yellow graph, and then our velocity right below it, there's a phase shift here of pi over 2, or 1/4 of a wavelength. And let me just kind of show that a little bit more clearly here, or attempt to. Here's our axis, and the green is going to be our displacement graph. Let's try this again just so we can have a full cycle. Okay, this is a full cycle. And in our full cycle, here is halfway. This is pi radians. That's half of the cycle. This is 2 pi. So this is one full cycle here. This is our displacement. Now, as we said, when the displacement is at its maximum, the velocity is 0. And notice that our velocity is negative here because our object is moving down. So then we're up to here, and then we're up to our maximum, and back down to 0. And we should see that it's what we call phase shifted by 1/4 of a cycle. Okay, so 1/4 of a cycle, 1/4 of 2 pi, so 2 pi over 4, just hit this math up real quick, or if we simplify that, pi over 2. So it's shifted, the acceleration, or the, velocity graph is shifted by pi over 2. Okay, it's phase shifted.